Okay, in this problem we have 3 wires. You can see 1 is a wire with the current coming out of the page, 2 is a wire with current going into the page, and 3 is a wire with current going into the page. So what we know about a current carrying wire, so this wire goes in and out of the page, and so we know the B field circles this. Let's just draw each one of these. I think I'll draw them over here. So All right, so I'm going to draw 1 first. And so if I draw, this is my y, this is my x-axis, this is 1. Just draw the x-axis like that. I'm going to have a B field, so let's do that circles like that. And if I have my thumb pointing out of the page, then my fingers circle this way, counterclockwise. And I know my B field here points up. So this is my B field. So that's for 1. Now let's look at 2. So I'll do, this is my 2. And again, I know I have a B field that circles like that. Not the best circle, but good enough. It circles like that, and because it's into the page, I point my thumb into the page. My fingers circle around the wire, so I know my current is going this way. And so over here on this side, right next to the origin, again, I'm going to have a force up. I'm sorry, a B field up. So this is my B field. This is B of 1. This is B of 2. And then B of 3 is further down, like here. It's an X. And again, I have a B field that circles it, so I'm going to have a circle that looks like this. And because it's into the page, my current's going to go clockwise. So I put my thumb in the direction of the current, my fingers circle. And over here, I'm going to have a B field that points like that. So that's going to be B3. Okay, so let's think about this as a triangle. So if I think about, I have the B field up in 2 places here. So I'm going to have, let's see, this is going to be my B1. And then I also have B2. This is my B2. And then I have B3 goes this way. So these are the vectors that make up my net B field. And now let's figure out how big they are so we can decide like what the scale of these 2 vectors are to each other. So I know my B field, the magnitude is equal to mu naught I over 2 pi r. So for 1, I know the magnitude, so B1 is going to equal mu naught I. And so I know that wire 1 and 2 carry a current of I, and that 3 carries a current of 4I. So my I for current 1 is just I over 2 pi, and then the distance away, right, is this distance here is the radius, and that's d, so 2 pi d. And now B2 is equal to mu naught, again this one is I, over 2 pi, and then the r again, right, this is going to be my r, and this is also d, so this is d and this is d. This is 2d. So this is going to be d, and then B3 is going to equal mu naught. Now my I here is 4I over 2 pi, and now my R here is going to be 2d. And I can write that as my 4 on the bottom and 4 on the top cancel, and I get mu naught I over pi d. So I'm going to write now B, the x component of B is going to equal to 2, is equal to B1 plus B2. All right, that just comes from here. My x, this should be my y component. Let's see if I can erase, maybe. Nope. All right, so we'll just fix it. So this is my by, because I have B1 plus B2. And looking at B1 and B2 here, they're the same. So I can just say that's equal to 2 times mu naught I over 2 pi d, which is really just mu naught I over pi d. And now bx is just equal to b3. So bx is equal to b3, which is equal to mu naught I over pi d. And that's really interesting now. Looking at these two things are the same. They're equal. So what that tells me is I have a B field where my x component and my y component, this is my by, this is my bx, and they're equal. And so that tells me that my vector, my net vector, looks like this, right? It's the resultant of this, of my little, now square, usually I would say rectangle, but square. So this is my b net. And that because by and bx are equal, that means this angle is 45 degrees. So, so if I want to write this out as a vector, which is what I need to do, so b is equal to mu naught I over pi d, and this is the positive x direction, right? To make up a vector that looks like this, I need to go over in the x direction and up in the y direction. So this is going to be in the positive x direction. So I'm going to have I is the x direction, I hat represents the x direction, plus j hat. And because that's the reason I pulled this out is only because my x and y vectors are equal. If I didn't have a 45 degree angle, if they weren't equal, I would have each one would have a component that would be different. And let's, just because we can, we're going to use it later. So later on in the problem, they give us all this information. So let's just calculate what my b, the magnitude of b is. So the magnitude of b is equal to, I can see mu naught I over pi d. So that's going to be 4 pi times 10 to the minus 7. I is 1 amp. We'll see that later, further down in the problem, divided by pi. And then d is 10. Or I think in this case it is, just see. Oh, it's 1. It's 1 meter. And so then the magnitude of b is equal to, the pi's cancel, and I get 4 times 10 to the minus 7 Tesla. And so I'm going to use that on part B, which is coming up. See if I can go down. Yes, I can. Okay, so we just finished part A, and we're going to start on part B. And this says, find the force on a charged particle passing through the origin with this speed, 1 meter per second, and the charged particle is out of the page, so it's moving out of the page toward us, and it gives us the value for the current and the value for D. So if I think about, redraw this of what we have right now, so this is our y and this is our x, and this is our b. So that's the b field that we have, and we have a, let's not even do that. Let's just draw our b field. We have a b field that's like this. It's 45 degrees. That's my net b field, and at the origin, so right here, it's coming out of there, there's a positive charge, and it's moving out of the page. So if I point my pointer finger at me, and then I rotate my middle finger so that it's pointing that way to the right, then my force is going to be up. It's going to be this way, perpendicular to B, right? So that's going to be my force. It's perpendicular to B. It says find the force. Okay, so at least now I know what the direction is, and this force, my direction is going to be in the negative I direction and the positive J direction. So if I think about this force, if I have a force that looks like this, or a vector that looks like this, the components that make it up go this way and this way. And so this is the negative X direction and this is the positive Y direction. So we just need to keep that in mind when we figure out the direction. And let's calculate the force. So the force on a charged particle is equal to QVB. And I can just say QVB. I don't have to worry about sine theta because it's perpendicular to B. And so that's going to equal 1 times 10 to the minus 6 coulombs times the velocity is 1 meter per second times B is, we learned that it's 4 times 10 to the minus 7 Tesla. And so when we do that math out, we get the force is equal to 4 times 10 to the minus 13 newtons. And now I can just plug in my direction. So I've got the minus I hat is my x direction. It's negative x direction plus j hat. And because my B was in the 45-degree angle, then I know that F is a 45-degree angle with respect to the x-axis here. Right? So I know my components are going to be the same magnitude here. And so that's why I can pull the magnitude out. Now let's see if we can go down. There we go. Right, so we want C. So find the force on a fourth wire with length 10 meters located at the origin. So we've added a fourth wire here. So we're adding a fourth wire, but we're not finding its magnetic field. What we're doing is we're finding the force on that wire due to these other wires. So I'm just going to stay with my B field right here. This is my B field. And now I've added a fourth wire right here. And it says that the current's out of the page, so it's going to be a dot. So it's just like the charge one we just did in B. And so we know if current's coming out of the page, we point out of the page. I need to rotate my fingers in the direction of B, my middle finger in the direction of B, and my thumb points this way. So same idea, that's going to be the same force, same direction for force. And again, I'm going to have negative x and y, positive y. And to calculate the force, I'm going to use I, L, B, and I don't need to do the cross product. You know, I am using the cross product because the sine of 90 is 1. So I plug in here, and I'm going to have 1 amp times 10 meters for L, that's what they tell me, and times B, which is 4 times 10 to the minus 7 Tesla. And the force then is in newtons, and that's equal to 4 times 10 to the minus 6 newtons, and my directions are negative I plus J. So that's it for C. And now the bonus, where could I place the fourth wire from part C so that the magnetic field at the origin is 0? All right, so for the bonus, we'll do the bonus over here. All right, so first thing I know is that I have a wire that has the direction is out of the page. And I want to, what if I place a wire in here? I'm going to want to, if I have a B field this way, I'm going to want to have, let's see, create a B field this way. So this one's going to be my new B field created by this wire. And I want this one to cancel, so I want them to cancel out, this one to cancel out that one. Great. So if I think about that, if this is my origin, then if I think about this, this is going to be tangent to a circle. So for tangent to the circle, if I have a wire coming out, I'm going to want the current to go this way. So I'm going to want to place a wire like here. And if I do that, then I will create current that comes around, that circles, and it's going this way. It's going this way. So this is tangent to the circle right there, and so that's where I need to place that. And because I'm still doing all 45 degrees, where am I going to place it? I'm going to place it at, let's see, see if I can find my notes on this. I'm sure this would give you partial credit. Oh, there we go. So what is my B field? My B field is mu naught I over pi d. And so how did I get mu naught I over pi d? If I think about my where I put my, I only have one wire, so I'm going to need to put it d 2d away. So I'm going to have, in order to get this, I'm going to have right, it's got to be I. So if in order to get this out, so that I have the same length of my magnitude here, I need to set this equal to mu naught I over 2 pi r. And what r will give me, so what I'm really doing is setting the denominators equal. So I'm going to say 2 pi r is equal to pi d. And so r then is going to equal d over 2. So in order to get that, so in order for that to be true, I'm going to need to be d over 2 away, which means this distance is going to have to be d over 2. And so if we want d over 2 away, then we can think about this as a 45-degree triangle. And so when we have a 45-degree triangle, we have 1, radical 2. So that means we would need to divide this by the square root of 2. So my x is going to be at d over 2 divided by the square root of 2. And y is going to be the same. And I know it's going to be located at, so the locations are going to be d over 2 radical 2 in the negative minus I plus d over radical 2 times 2 in the j hat direction.